The quicksort is a powerful, fast, and efficient comparison-based sorting algorithm that partitions an array and then recursively calls itself on each resulting half. This is also known as the divide and conquer strategy for sorting data. So what is partitioning? Partitioning takes an array, chooses an element to be the pivot, then puts each element smaller than the pivot on the left side of it, and each element greater than it on the right. It's important to note that partitioning doesn't fully sort the array. The elements smaller or greater than the pivot will still probably be out of order. It only guarantees that they'll be on the left side or right side. This is okay because the quicksort algorithm can recursively call itself with all the elements on the left of the pivot as its own input. It does the same with all the elements on the right, and this eventually results in a fully sorted array.
Alright, let's take a look at the code now. And this is our quicksort function. Takes in an array, and it takes in the first index and the last index of said array. So we're partitioning our array, and then we're calling quicksort on two halves of it, and I'll show what that looks like a bit later. But let's take a look at this partition function. All right, this is the partition function. But before we start, this is important. So this is what the book suggests. This is code from the book, and they just use the pivot as the first element in the array, and we'll explain why a bit later, why this might not always be the best thing to do. But with small data sets, it's perfectly fine, and in most cases, it's perfectly fine. But just keep that in mind, and we'll get back to that later. So this algorithm does something interesting, and it uses something called a two-pointer approach, which is what these two variables are up here. And it's not pointers like in C with memory and stuff. You know, it's pointers like pointing to the index of the array. So you can really just think of these as indexes, right? So the low index is like starting from the left and traveling to the right, and this high pointer or index is starting at the end of the array and traveling left. So that's why we pass in these. And the low actually starts with the second element, not the first, because this is using the first element as the pivot, and so we don't want to compare that, so we just set it to first plus 1. So this first while loop here uses our two index pointers to basically put elements that are less than the pivot on the left side of the array and elements that are greater on the right side of the array. So it does this with the while loop. And this first one, what this does, and I'll actually open up a little diagram here to demonstrate. So this low pointer is going to start at the second element because this is the pivot, and I'll use a different color like red to show the high pointer, which starts on the last element. So what this while loop is doing, it's traveling to the right until it finds an element that is greater than the pivot. So if we do this, okay, we start on one that's greater than pivot 6. 6 is greater than 4, so we exit this while loop, right? We go to the next one, which decreases the high pointer. It moves it to the left until it finds something less than the pivot. 1 is less than 4, so since we've already found both of these, if high is greater than low, in this check, all this is really doing is making sure that the lower element is on the right and the greater element is on the left. And this is just swapping the two of them. So we've swapped the two of them. And these pointers remain in place, and we go to the second iteration of the while loop, etc., etc. I won't read every single line, but I'll basically show you what happens, right? This left pointer here is going to travel to the right until it finds something greater than 4. And then this high pointer is going to travel to the left until it finds something less than 4. It's going to travel here. But because high is now in this case not greater than the low pointer, if you can see they've overlapped, we're not going to do anything. And this is really because we've already accomplished our goal, which is if we ignore this first element on the left here, we've put all the lower elements on the left side, 1, 1, 3, 2, and we've put all the greater elements on the right side. So now the last thing to do is put this 4 into the correct place. And so that is what this next while loop is starting to do. It's taking the high pointer, which I believe was on this element right here, and it's subtracting it until it finds an element less than the pivot. which it's already done, it's 2. What we're going to do now, if pivot is greater than this, which it will be, because that's what this just did, we're going to swap the 2 of them. You can see, we're going to swap them. And what that does, essentially, is this. We have now created an array where this is the pivot, and every element to the left of it is lower, and every element to the right of it is greater. And then we return, all this is doing is returning the index of this pivot so that we can recursively call this function on, say, the left and the right. So it would return 0, 1, 2, 3, 4, and then we would call the quicksort algorithm again. Like, for example, we would call it on this array, and this would repeat recursively. This would be the new pivot, and it would order itself until the whole array is sorted. So I've actually gone ahead and shown this. This is the array that I was just working on. And so if we take, 3 was the index, and if we take the left half of that and use this new array as input, with 2 as the pivot, it sorts itself like this. And recursively now we go back to the right half of the array where 4 is the pivot. Nothing changes, but this is a recursive function, so this happens again with 8 as the pivot, and it sorts itself like this. So by the end of this, and it's important to remember that this is all happening in place. It's not creating new arrays and sending that, it's just changing the indexes of where the partition algorithm should start and stop. But anyway, if I kind of drag these back together, we will see the end result of the array, and as you can see, 1, 1, 2, 3, 4, 6, 8. It is now sorted.
Advantages of quicksort. It is a divide and conquer algorithm that makes it easier to solve problem. It is efficient on large datasets. It has a low overhead as it only requires a small amount of memory to function. Now I am going to talk about the disadvantage of quicksort. It is not a good choice for small datasets. It is not a stable sort. It has a worst case time complexity of order of n square, which occurs when the pivot is chosen poorly. Quicksort work fast and efficient for array, especially for large dataset. So we can say that for small dataset, quicksort is a bad choice. Secondly, quicksort is not a stable sort. Why? I'm gonna explain. We can see an array and it has same value 5. I distinguish them 5 and 5 prime. So the first row is unsorted array. And in second row we can see is a stable sort, and 5 and 5 primes are sorted by their original positions. But in third row we can see 5 and 5 prime are not sorted by their original position, so we can call it unstable sort. So why quicksort is unstable sort? Because it doesn't maintain the original order of the duplicate element due to swapping. So we can see in the third row has an unstable sort because quicksort swap element according to pivot's position.
What is time complexity? An algorithm's time complexity is a numerical representation of how long it takes the algorithm to execute in relation to the length of the input. The length of the input determines how long the method takes to run, not how long the computer takes to execute the algorithm itself. An algorithm's time complexity is the amount of time it takes to solve a certain task, in this case sorting. The quicksort algorithm partitions an array, then makes a recursive call on both the left and right half of itself. This results in a time complexity function that looks like this. Partitioning takes n time because it loops through the array once, and the 2 recursive calls can be represented at the time function with its input size halved. The total time therefore equals the time required for each half of the array plus the time required for partitioning, where one half of the array would require the time of a fourth of the array plus n over 2, because the time required for partitioning is halved because its size is half that of the original array. The sum of this resembles a geometric series that adds up to O n log n during both its best and average case inputs.
Now I'm going to talk about worst case time complexity of a typical implementation of quicksort is O(n) to the power 2. The worst case occurs when the picked pivot is always an extreme, smallest or largest element. This happens when the input array is sorted or reverse sorted and either the first or last element is picked as a pivot. Here we can see this array is already sorted. I'm going to select 1 as a pivot element. Less than 1 elements will be in the left side array and greater than 1 elements will be in the right side array. We do not have any less than 1 elements, so left side array is empty and everything will be in the right side. Next, I will select 2. We do not have any element less than 2, so left side array will be empty again and everything will be in the right side. If we continue to select the first element because it is already a sorted array, we find all left side array empty and everything is in the right side array. The partition of algorithm will take time for this array is n. We have nothing in the left side array. So the partition of algorithm will take time n-1 for the next one. If we continue like that, we will get n-2, n-3, n-4, and n-5 for all. Now what is the time complexity? We have to sum up the time. We get 7 for n, 6 for n-1, 5 for n-2, 4 for n-3, 3 for n-4, and 2 for n-5. We have to sum up the natural number. It is not starting from 1. It is starting from 2, so we have to subtract 1. Here we have to ignore constant term. It will be n square plus n. We have to consider the higher order term, so the time complexity of worst case in order of n square.
Like we have previously shown, the efficiency of quicksort relies heavily on the importance of pivot selection. The graph shown on the right presents an array that uses its first element as the pivot for this example. As you can see, the algorithm repeatedly selects the first element as the pivot, leading to subproblems that are not effectively divided. This results in a situation where the algorithm makes a large number of comparison and swaps, leading to the worst-case time complexity of 0 of n squared. In the previous slide, we saw how the choice of the pivot can affect the efficiency of quicksort. Here we take a different approach by selecting a more balanced pivot element, such as the middle element, or 3, from the array. By selecting a better pivot, we avoid the worst-case time complexity and improve the overall performance of the quicksort.